Okay, so now let's see the calculation of this probability that we discussed last time. Um, in this example of the lady tasting tea, right? So let's stick with this test, which is checking if the number of correct answers is at least 6. Okay. Okay. So let's write out the answers, right? So what is probability that t equals 8 conditioned? So here all these numbers are conditioned on the lady guessing randomly. Right, so you could ask, okay, so what exactly is the probability that that she gets all the answers right if she was guessing randomly? Okay, so this is now a combinatorial problem, right? So she is presented 8 cups, okay, and there are some 4 A's and 4 B's, but of course these are in completely arbitrary order. And you can think of this problem as just, she picks 4 of them. And what is the probability that those 4 are the A's? Okay, and for this you can write out an expression, but the point to note is that this is some non-zero value. Okay, so this may be small, but it's still non-zero. Okay, so there is always some chance that even under the null hypothesis, you get t equals 8. Okay. And likewise, you can ask, okay, so what is p equals 7? Okay, t equals 7. Okay, so this is actually a trick question. So it turns out that this probability is 0. Okay, and that's just because the number of correct answers can never be odd. Okay, and that's because you have 8 cups and you know that 4 are A and 4 are B, and if she chooses exactly 4 and thinks that they are A, the number, you can easily verify that this number can never be odd. Okay, so that's a simple exercise. Okay, so right, so likewise, probability of t equals 6 will be something, t equals 5 will be 0, and so on. Okay, so these are some numbers that you can compute, and the way to compute them is exactly as I said before. So you say that, okay, so what is the probability that she got all 4 of these correct, something like that. Okay, so let's not see how to compute these probabilities, but let me write it. I have cheated, and for those of you who want to know exactly what these are called, this is called the hypergeometric distribution. Okay. You can also estimate these probabilities in R via simulation. Okay, so that's another way to get these numbers. Okay, but yeah, in this case there's a simple formula for this. Okay. But I'm not deriving them because the point of this lecture is not to derive these kind of numbers. Okay, so trust me with these values. So you get that the probability that t equals 8 is something like 1 by 70. Okay, and this is a number that this is like 0.0143, something like that. Okay, so this is a little bit more than 0.01. Okay, and these are what they are, right? So these are like quantitatively the numbers. Couple of things to note. So one is that there is a 1 by 70 chance that even if the woman is just completely randomly guessing, she gets all 8 cups correct. Okay, depending on your outlook, you may think that this is a fairly large quantity. I mean, there's more than a 1% chance. But then of course, you know, in reality 1% chance is pretty small, right? So you are willing to bet against this happening, right? But if you set your threshold, right, so suppose our test was checking if t is more than or equal to 6, okay, then there is a 17 by 70 chance. Okay, so this number is you know, it's a little, it's more than something like 28% or something. Okay, so you should check this, but I think so that's what it comes to, and there's more than 28% chance, yeah, maybe 24% chance that condition holds even if person, even if lady is randomly guessing. Okay. And these may not be the kind of odds that you're very comfortable betting against, right? Because you know that there's a 24% probability that she succeeds even if this were completely randomly guessing. Okay. So this testing if t is bigger than or equal to 6 is a weaker test than a test that checks if t is more than or equal to 8. Okay. It's weaker in the sense that the condition of this test could hold with a higher probability even if this person was randomly guessing. Okay. T bigger than or equal to 8, the probability that the person succeeds if she is randomly guessing is something like 1.4%, okay, which you may be comfortable with, while 24% is usually quite high. Okay. And likewise, so yeah, so another fun fact with these numbers is that the probability of getting t equals 0, which is everything incorrect, is exactly the same as the probability of getting everything correct, which is not surprising. If you are randomly guessing, you are equally likely to be like super lucky as you are to be super unlucky. Okay, so that's why these numbers are the same. That's why there's a symmetry here. Okay, so this is an example where we realize that this is a much more conservative test, t being bigger than or equal to 8, conservative test. Six, right? In the sense that here the probability that a random guesser would succeed is way lower than this. But this is of course as is to be expected, right? Now this probability value, the probability that that this condition holds under the null hypothesis, this is often referred to as the alpha. Okay, and this is like the statistical, this is the quantity that we defined over here, this is the significance level of the test. Okay, so this quantity, which is significance level. Okay, so let me put this in box so that you don't get confused. Okay, so significance level of a test, so this is the probability that success condition holds under null hypothesis. Okay, so that's called the significance level of this test. Okay, and usually you would like the significance level to be a small quantity. Okay, so there is one point that I kind of missed here. Okay, so which is that it is very important in statistic in hypothesis testing that this test, the test condition and the test criteria and the test statistic must be chosen before actually seeing the outcomes. Okay, so you can't observe what you got and say, hey, this is very unlikely that I got this precise set of outcomes. Okay, and therefore I'm going to reject my null hypothesis or something. Okay, so it's very important that the test must be chosen before actually seeing the outcomes. Okay, and then you actually perform the experiment, get to see the outcomes, and perform the test that you had decided to do. Okay, and so this is a very important point to keep in mind. Okay, so all right, so let me now go to a second example. Okay, so and this is, I don't know if you saw this, if you know about this fact, but people observed that if you look at a penny and a specific kind where there is a Lincoln photo on one side and there is a picture of the Lincoln Memorial on the other, so apparently, I have not verified this, that the probability of showing up heads is like 80%. Okay. Okay. And suppose somebody told you this fact, right? Like, in this case, the probability that it is that you get heads is like more than 75%. Okay, maybe not the exact number 80%, but somebody told you that this is more than 75%. Okay. Now the question I'd like to ask is, how do you verify this, right? So what is a good statistical test? And how do you analyze this test? Okay, so let's follow this paradigm that we set out last time. You've got to first formulate a null hypothesis and you've got to formulate an alternate hypothesis, right? So what is the null hypothesis in this case, right? So somebody is claiming that the bias, which is the p, probability of heads, is more than 75%, right? So a reasonable null hypothesis is to say that, okay, I don't believe you, right? So this is, this coin has a bias that is smaller than or equal to 3/4. Okay, so that is one natural null hypothesis. You could also, in this case, have a null hypothesis that says p equals half, right, which is saying that the coin is actually fair. Okay, so both of these, I'd like to point out that these are actually valid null hypotheses. Okay, so you could have p equals half as your null hypothesis, but but very often in hypothesis testing, you somebody makes a claim and you set your null hypothesis that is intended to violate the claim. Okay, so maybe not just what you might expect about the ideal behavior, because when you say that your null hypothesis p equals half, you're bringing in some inherent information about coins to the picture. Okay, so you're not just trying to violate, you're not just trying to verify if this person is saying is right or not. Okay, so some people stress this point a lot. I'd like to think of both of these as kind of valid null hypotheses. Okay, so but let's stick with this one for now. Okay, so your null hypothesis is that the coin has a bias p which is smaller than or equal to 3/4. Okay, and your alternate is what the person claims, which is that the coin has p which is more than 3/4. And what is a natural experiment that you would do? Of course, you toss the coin a bunch of times. Let's say we toss the coin 20 times. Okay, and now we will. What is a good statistic? right? So if you toss a coin 20 times, you will see outcomes x1, x2 up to x20. These are heads or tails. Could call them 1 or 0 if you want. And what is a good statistic? A good statistic, t, not to be confused with tails, is the number of heads observed, right? And what would be the form of this test, right? So the form of this test would just be, you would check what is a reasonable form of a test, right? So if p is in fact more than 3/4, right, you would expect to see a lot of heads. But on the other hand, if p were less than or equal to 3/4, you don't expect to see a lot of tests, a lot of heads, right? So remember, your goal is now uh, to see if you want, to build evidence against the null hypothesis, right? So your null hypothesis is now that p is smaller than or equal to 3/4. You'd like to build evidence against it, right? So if you toss this coin 20 times and you saw 20 heads, all 20 are heads. Okay? Now that's a very strong evidence, or fairly strong evidence against the null hypothesis, right? Because if p were actually less than or equal to 3/4, it's quite unlikely that you saw all 20 heads. Okay? So your form of the test is going to be t is bigger than or equal to some threshold. Okay, so that's what we will write over here. Okay, so the null hypothesis will be exactly this thing which we said, coin has bias is equal to 3/4. Test statistic here is this, and the test is check if t is more than c for an appropriately chosen threshold c. Okay, and now the question is, how do you pick c? More importantly, how does the choice of C affect your calculations? Okay, so let's see that in a little bit.